This is Sanket.
Hi, this is John J.
Today we are going to present to you an integrator-based LDO which we fabricated in 180 nanometer technology in the class E6350 VLSI Design Lab at Columbia University, and it's an integrator-based LDO which is built using a differential VCO, and it's built to support a dropout voltage of 100 millivolts at a low power of 3.6 microamps.
Thank Moses for making the chip fabrication possible, and thank Electrical Engineering Department at Columbia University for providing the test equipment.
So in this presentation, we are going to explain how an integrator-based LDO works as compared to our traditional designs, and then we're going to show you on the bench how this LDO performs. Hi, so I'm quickly going to explain how the LDO works before we see the demo. This is the traditional LDO, which uses an op amp which provides the gain for this LDO to work. So this, as you can see, it uses CC and RZ, and the op amp provides the gain to regulate V out equal to Vref. The trade-off of this circuit is that the gain is limited at DC, and hence you get a finite error at the output, which is determined by A upon 1 plus A. Now the integrator-based LDO, on the other hand, doesn't use an op amp, but it uses two VCOs in a differential VCO setting, and what it does is it converts Vref and Vout into frequency information, which is compared through PFD and charge pump, and then which are equalized through the circuit. As you can see, the Bode plot of this case, you can see there is an infinite gain at DC, and hence you can get a very good accuracy at the output. Also, because of the integrator-based operation, there is much lower power, and hence it can support higher efficiency. Because of the digital control loop, it's very easy to do external control of parameters such as bandwidth and phase margin.
I'm John J. Today I'm going to demonstrate you how our VCO-based LDO works. As you can see, this is the PC board we designed for testing this chip. Sitting in the middle is our LDO chip, and this is the potential meter. We're going to tune in later for the change of loading current. And these two are the multimeters. These two are the DC voltage supplies. This is our V-in, which is going to be the VDD of circuit. Right now this is 0.8 volt. And this is our Vref, and then it's set to be 0.7, which means the dropout voltage is 0.8 minus 0.7 to be 100 millivolt. And Vout is supposed to be tracking the Vref, which is the output of our circuit. And that's how basically we want for a regulator. And this is the V gate, which is a power MOS gate voltage. And okay, I'm going to start tuning this potential meter here. And we can see a change in the current here. As the current starts to increase, we can see that Vout is still following Vref quite well. And we can see a drop in the gate voltage. And as we reach to the maximum setting of 60 milliamp, we can see that the V gate is almost hitting ground, and Vout is still able to follow Vref pretty well. Okay, so this is the short demonstration for the 60 milliamp 100 millivolt dropout LDO. Thank you for watching.
So this is Sanket, and what I'm going to do is quickly show you another feature of this VCO-based LDO, which is sitting right here. As you saw earlier, the V-in or the VDD was actually 0.8 volts, and the Vref was 0.7 volts, and it was able to regulate up to 60 milliamps of load current. So as you can see here, the VDD has been increased from 0.8 volts to 0.85 volts, and Vref is still the same. And as you can see, the load current is 100 milliamps now, and it can still able to track exactly. So Vout is exactly same as Vref, and it can support up to 100 milliamps for a 100 millivolt dropout, 150 millivolt dropout. This is the operation of our VCO-based LDO, and what it can do is it can support 60 milliamps for 100 millivolt dropout and 100 milliamps for 150 millivolt dropout.